So you may be wondering, why am I starting off a welding video with showing you eggs? Well, I can't like eggs.
Is that like a personal attack or something?
No, I'm just kidding. There's a real reason why I'm showing you eggs. But let me eat my breakfast first and I'll explain. I want to start off by talking about the simplest welding rod you can make. Now, there are many materials you can use for welding rods, but this patent used paper to cover the rod and sodium silicate to soak the paper. Now, sodium silicate is also known as water glass and is primarily used as a high-temperature adhesive. And when you look at other patents and sites, you'll find it is mentioned as a commonly used binder in the manufacturing of welding rods. As you can tell, there are many different materials we can look at and talk about when it comes to this, and each material has its own purpose. It gets pretty technical, but let me just bring to your attention one more ingredient that I want to talk about, and that's calcium carbonate. Calcium carbonate, also known as limestone, is pretty interesting because of its properties. At high temperature, it breaks down into calcium oxide and carbon dioxide. In welding, carbon dioxide is a shielding gas, and interestingly enough, calcium oxide is also useful as a sort of fluxing agent. It's used in steel making to remove impurities in the molten metal and create a protective slag. See, when you weld, the ingredients used for the coating of the rod will each have a purpose. There are alloying elements and deoxidizers, binders, shielding gases, arc stabilizers, fluxes, and slag formers. Now, to sum this all up, we are going to be using paper, sodium silicate, and calcium carbonate to make our rods. So my idea was to follow the first patent I showed you and make a pure sodium silicate based electrode and see how it performs. Then we will add the calcium carbonate and compare the performance. Now, silica gel, the stuff you find so commonly in shoe boxes and packaged items, is made from sodium silicate. And we can actually turn it back into sodium silicate by combining it with sodium hydroxide, otherwise known as lye. As for the calcium carbonate, or limestone, well, that's literally the main component of eggshells, hence why I showed you the eggs in the beginning, so I'll be using that. So to make the sodium silicate, I took the silica gel and shredded it in a coffee grinder. This will make it easier to mix later, but you seriously do not want to breathe this stuff in. I wore a mask and very carefully handled the powder, letting it settle after shredding before I put it all in one glass container. I also cleaned the eggshells by rinsing them first in warm water and drying them out. Then I also shredded them and later baked them at 450 degrees Fahrenheit for 30 minutes. That turned them into a nice golden brown color and got rid of any smells. Because there were still large chunks in the shredded eggshells, I decided to put them through the coffee grinder one more time, and that created a much nicer powder than before. Alright, so back to the sodium silicate. I measured out 12 grams of silica gel, 16 grams of lye, and 30 milliliters of water. Now, the proper stoichiometric amount is 80 grams of sodium hydroxide to 120 grams of silicon dioxide. But sodium silicate doesn't seem to care about stoichiometric ratios, meaning all ingredients are not completely consumed in the reaction, and you can play around with the amounts as desired for different results. It's also generally recommended that for refractory uses or for high temperature uses, a more silica-rich mixture be used, like the one I'm showing you now. But for amateur uses, a sodium-rich mixture will work just fine. I used a 2 mole sodium hydroxide to 1 mole of silicon dioxide ratio for my mixture. I hope I didn't lose anyone in all this. I just wanted to explain where my numbers are coming from. Now, I'm using a steel container for this. Anything aluminum will get eaten by the lye, and we don't want that. So first I made sure my water was warm, then added the lye and stirred till it was completely dissolved. And then I added the silica and stirred till it was completely dissolved too. Now we have this dark watery mixture, which is fine. I mixed a lot of different silica beads together, so that's probably why I'm not getting a clear solution. I also did use a little bit too much water, but you do want the solution to be more on the runny side so the application process will be a little bit easier. If you need to thicken the solution, you can always heat it a little longer to evaporate more water. I think it's about time we get started on the rods themselves, and I began by unfolding and initially straining these coat hangers out with some pliers. After that, I cut it into 9-inch long segments. That's about 23 centimeters. There was some excess, but I kept that on the last rod because I didn't want to waste any material. To straighten out the segments more, I used my bench vise, and that worked great, but it wasn't enough. I decided a practical test to check if the rods were truly straight is to try rolling them in between two panes of glass. A fairly straight rod will want to roll in between the glass, but a rod that isn't straight will drag itself in between the glass. What I did to finally turn these rods straight is, well, actually turning them. Yeah, I attached one end to my drill and one end to the bench vise, and I very slowly turned the rod a few times. This actually creates internal tension in the rod that straightens itself out, and after I did that, all the rods passed my glass pane test. I also marked about 1/2 inch of space at the very end of each rod too, and got rid of the coating by using my drill and some sandpaper, and when that wasn't enough, I used a bench grinder instead of sandpaper. Now to wrap these rods, I'm using this paper that was used in a newspaper printing factory. These are nice because they are long and I can cut long strips from them. The strips I made were 36 inches long, and I experimented with the width. At first, I cut inch-wide strips until the wrapping became too difficult, so less is really more in this case, and I cut the strips in half lengthwise to give me about 1/2 inch wide strips, which were much easier to wrap around the rod. I also found a little bit of super glue at the beginning and end of each wrap is really helpful. Now a little side note here. I'm wrapping at about a 45 to 30 degree angle. I noticed a sharper angle gives a smoother but thinner wrap. You will just have to experiment with the technique a little bit to get good consistent wraps. So this is how they came out, and you can see the difference between the rods on the left that were wrapped in 1-inch wide strips to the nicer rods on the right, which were wrapped in 1/2 inch wide strips. Now we can begin soaking these rods in the sodium silicate. I tried a brush, but it literally melted in the solution, so I found the best way to handle the solution was with a glass dropper, and to place the rods on a steel sheet while you use the dropper to make a puddle around the rods. I'm making a puddle because the paper doesn't instantly soak up the solution and just needs time to do so, so I saw this as the best way to soak the rods. I want to also add that I tried soaking the paper as I wrapped the rod, but once you wet the paper, it loses a lot of its strength and tearing is more likely to occur, so I don't recommend this method. I then put the rods in the oven, set the temperature at 300 degrees Fahrenheit, and let it bake for 1 hour. After the rods were dry, they were ready to weld. So this is how they came out, and I just want to give my initial thoughts on these before I start welding with them. Now there's two things I want to point out. One being that they were dried, but after a very short amount of time, they like to absorb or adsorb, yeah, that's a word, adsorb moisture. And so I think that's just to do with the sodium silicate. I think it likes to absorb moisture. So because of this, I think I'm going to actually reheat them and dry them out again before I start welding with them. Now the second thing I want to point out is that you can see a clear difference between the skinny ones here and the thicker ones. And the thicker the wrapping, or the wider the strip that you use, because I used, let's see, so I used these wider strips, which are about 1 inch wide. I used them on these 3 rods, and you can see how they turned out. There's less uniformity along these rods compared to these ones, and the skinnier ones I used about a 1/2 inch wide strip. to cover them, and I think this is going to result in better performance in the rod. But we'll see, of course. I just noticed that when I looked at these thicker rods with less uniformity throughout the entire rod, I noticed cracks, actually. And I noticed in these rods, because of the thicker wrapping, the wrapping was simply not like tight enough around the wire, around the metal, and it was causing air gaps in between the metal and the wrapping. And so that's what you don't want. You want as much uniformity throughout the entire wrapping, and so I think that's why these are going to give the best performance, but we'll see in a second.
Okay, so reviewing the footage, I noticed two things. The rod is f***ing burning up while I'm welding, but a more important detail being that the arc is struggling to maintain a connection with the metal. Just listen very closely to how the arc starts, dies, and restarts while I'm trying to weld.
Alright, before I start talking about the welds, I do want to say I am welding these plates together, these types of plates. They are approximately 3 or 4 millimeters in thickness, or about 1/8 of an inch in thickness. And yeah, they're probably mild steel. I'm not an expert in steel grades, but I'm guessing this is just your common average type of mild steel. Nothing really special about it. I actually cut these sections with a plasma cutter, and this steel comes from a long L bracket. And obviously it's been outside, it's very dirty. But yeah, you know, it seemed like a good average common steel that would be easily weldable. I do want to mention that for all of the tests that I did not bother cleaning up the metal at all. I did not treat the metal, I did not heat up the metal, I didn't do anything to it. So I just wanted to get that out of the way. Alright, so let's start off with my control. So this is my control. These welds were done by this rod. This is most likely a 1011 rod. I think this might be a calcium carbonate based rod. And you can see that the weld is consistent, it's uniform, it has sort of a nice pattern to it, which also indicates that, you know, I was going in a consistent manner along the weld, and yeah, and it seems like it did join the two pieces of metal pretty well. And there we go, on the back side I cleaned it up a little bit, and you can see more of these really nice colors. And yeah, this is a really consistent weld. This is by far the best type of welding I have ever done with stick welding. So I'm really proud of myself for this. Alright, and here's what I welded together with the sodium silicate rods. Oh, I might have left that on, sorry. Right, so these sodium silicate rods were actually pretty interesting. They did give me decent results. Now, first of all, notice how the plate itself has a lot of soot, a lot of ash on it, and there's barely any slag. There's, well, no slag at all. I did notice with these rods it was much harder to start with them, but once you did start a weld with them, then I found that the arc itself was stable enough to continue welding. Now, when I welded with these rods, I found that doing a circle motion was just not possible. It was difficult to do that motion, so what I did with these rods when I welded, I actually just went very slow and steady and straight, and I made sure to keep an even distance, a uniform distance above the joint, and just try to fill in the joint with the coat hanger wire. That seemed to work the best with these rods. I noticed with the thicker wrapped rods that it was harder to get them into the joints because I had to push into the joints more with a bunch of unburnt paper in the way, and you know, this stuff doesn't burn off quite as easily if you have a thicker wrapping of it. So this is from the sodium silicate rod. You can see there's a little bit of porosity, yeah. But for the most part, it did provide a solid weld. Maybe it's not the most consistent, right? But at some parts, it did pretty well. This is the commercial 1011 rod. As you can see, obviously the welds are more consistent, and you have better adhesion, basically, just connection between the two metals. You have, of course, no porosity as well, or very, very little porosity. Oh my God, that's hard. And this, my friends, is exactly how you know you made a great weld, when the metal breaks right before the weld, and the weld itself doesn't crack or break. Alright, next up are these sodium silicate pieces that I welded together. There we go. Alright, so here's what happened. This broke, this broke, this broke, and this broke. But somehow, this survived. This held together, and look, all I can say about this rod is that it's a little bit inconsistent, but it all depends on how you construct this rod. One thing is for sure though, this does beat welding with a bare wire.
Now I went back to making more rods, wrapping all of them correctly this time and adding 10 grams of calcium carbonate we prepared earlier, which when mixed in the solution looked like this. It thickened up instantly, and now I could coat the rods using a glass stirring rod instead of a glass dropper. After baking the rods, this is what they looked like.
So I just took these rods out of the oven and they're completely bone dry. And immediately what you can see is that most of these rods look really good. But as you can see, I did try experimenting with coating just a bare wire with the solution because it was sticky enough and it was like thick enough. And so I thought it would stick to just bare metal well on its own, but that wasn't the case. Now, even though the solution did not stick very well on single bare metal wires like this, it did surprisingly well on 3 wires that I put together. Here, I'll try my autofocus, but as you can see, I wrapped 3 wires together and I didn't use any paper. And of course, when I dried out the rod, some of the solution stuck onto the metal sheet itself, and that's why it came off. But overall, you can see on the other side, it is pretty uniform. The coverage is pretty uniform on this rod. And it makes me think that, you know, if you twist maybe not necessarily 3 wires, but like, you know, 2 wires together, that might be enough to just give you a certain like trench, as you can see, like in between the wires to hold the solution there and hold it in place for it to dry out. Even though I didn't want to use paper on this new batch, I found that it's probably best to use paper anyway, just because the paper helps to absorb that solution and help it keep it in place. Now, I didn't want to use paper only because that most modern commercial rods, I think, don't use paper that often, right? But because we're making our own homemade welding rods and we don't have any special equipment, I think using paper is probably for the best anyway. So these are the 2 first plates that I welded with the homemade welding rods, and man, I am impressed. I'm honestly impressed. Maybe I'm too easily impressed, but these welds for a welding rod that I made myself are actually pretty consistent. You can see that we still have some porosity in the welds in the beginning here, but I was still trying to figure out how to properly weld with these. And then as you go along to the right of this plate, you can see the weld's getting, more consistent, slightly better. So here's more of a close-up on these good welds. And actually I found with the welding rod that I made, I had to go at quite an angle, maybe like a 45-degree angle, which I think is probably standard for, most types of welding. However, some commercial rods advertise that you can weld with them in any position. Now, I don't think this is the case with these particular rods. These rods that I made myself are best when welded with an angle. So yeah, all I'm saying is I had more control and an easier time welding when I welded with these rods at an angle compared to straight on top. But I want to point out, at least with these two plates, where I got good penetration, you can easily see in the back of the plate some discoloration. And these rods do penetrate into the metal, so it's actually way better than before, way better than the first batch of welding rods I did. All right, now if I get lucky and I start scraping this, maybe some slag will fall off, and basically I can show you that there is some slag on this. All right, yeah, there we go. That might not be the best looking bead ever, but coming from a homemade rod, I think that is impressive. Now, I also want to point out, because the welding was overall much better than last time, I was able to do a circle motion like this while I was welding, and actually take my time with filling the material into the joint. And it kind of shows in these welds. I mean, they're not perfect by any means, but you can see that I did get to fill in the joint as well as melt both pieces of metal, both plates. Yeah, that didn't take a lot of effort. Huh. That actually feels... That doesn't feel brittle at all, actually. It didn't crack or pop off. And it's actually still pretty solid. So instead of breaking, it actually bent. Alright, so all of these broke, and I think I know what the problem is. Upon closer inspection, all of these guys broke at the weld joint, and I think it's because I just didn't put enough material in the joint. So it really wasn't the welding rod's fault, it was more of my fault for not filling the joint in with more material while I was welding. Alright, so you can see the top plate here, we had really good fusion with the weld, but the bottom plate not so much, right? And that's where it kind of failed. So all in all, I think the rods are amazing for being homemade, obviously, but just because the homemade rods were very thin, it made it a little bit difficult to weld for me. Maybe there's a certain learning curve when it comes to these homemade rods that I haven't figured out yet, but that was my last rod, so I think I'm just going to end the video on this note. But for anyone that wants to try something like this, I think you will get better results if you try thicker rods. I think thinner rods are maybe a little bit more problematic. So coat hanger wires might not be the best to make into welding rods, but as you can see, you can weld with them. So you may be thinking to yourself, Matt, you're reinventing the wheel. Well, yes. But we wouldn't know how far we have come if we don't acknowledge and learn about the fundamentals. Obviously, complexity is grown over time, and by this point we have pretty much perfected the welding rod. but I still don't think we should take it for granted. It's the same idea with people that are born and raised into a world where they have everything at their fingertips without ever realizing how much research and development went into making those things. So my argument is, why not go back to the fundamentals and give yourself a sense of perspective? Yeah, so I hope this is helpful to somebody. I'm a little bit frustrated only because I wanted good results to show you guys, but I've been getting very inconsistent results with the homemade welding rods. And I think that just may be because I haven't done enough tests. I think I pretty much nailed the solution and the application of the coating, but it still needs a little bit of work. I feel like with thicker rods, this might work a lot better. I was really hoping for these types of welds from the homemade welding rod, but I guess that's not going to happen until you really perfected the welding rod. I mean, there's still loads of variables, so I guess, you know, I still am impressed with my results, but there's many more things you could try. You could try changing the solution a little bit. You can try changing the way you apply the solution to the rod itself. You can use less paper, for example, and maybe that would help with welding better. You can use thicker rods. You can weld DC electrode negative instead of DC electrode positive and see how that compares. You can change the type of steel you use to both weld with and weld on. So, you know, I can't test all of these things. So as always, I hope this was useful or helpful to somebody, and I'll see you in the next video.